some examples. Okay, and the learning outcome, investigate neural network and genetic algorithms and also genetic programming. Okay, I will see all these topics in the next slides. Okay, so here artificial neural network. As I said, again I'm repeating my words which I started. So here artificial neural network, it reads the features from input data and it processes the features and process the features with some action functions, and then it produce some output in the form of classification. Okay, so here neural network generally applied when the features are real valued, discrete valued, and vector valued. Okay, so here when the training examples are training examples will be classified based on these features. Okay, so here in, when compared with previous algorithms like finders algorithm and other previous algorithms, traditional algorithms, decision tree algorithm. So here artificial neural network has an advantage. It can target with vector values. Okay, so here the artificial neural network can be implemented in complex real world where an array of sensor data, where complex data can be collected from large sensors. Okay, so in that case, in complex scenarios, we generally go for artificial neural network where we collect a large data values. Okay, so here in advanced neural networks, we go for back propagation where more accuracy can be achieved. Okay, and next, so it is basically an information processing paradigm. Okay, and this artificial neural network in most of the literature, it is given that the artificial neural network is inspired by biological nervous system. Okay, as in the biological nervous system, in artificial neural network also, there will be multiple neurons which will take the features from the input training examples, and the data will be processed and the data will be classified. Okay, again I'm repeating. Okay, so here in as like in brain nervous system, human brain nervous system, here also you'll have a complex interconnections between these neurons for processing of the input data, and after processing it will produce the output. So when you discuss about human brain, and an interesting thing that is uh, human brain can uh, take the decisions in a fraction of seconds, like 10 power minus 3 seconds, when compared if you compare with a computer, high speed computer, the computer can take decision in 10 power minus 10 seconds, so which is very faster than the uh, an, uh, uh, human brain neuron. So here uh, so the computer switching speeds are very high uh, when compared with human brain neurons. Okay, that is in the case of complex scenarios. So for suppose when you take identification, for suppose a human identification of a regular person like a mother. Okay, so human brain can take decision, can identify the person mother in 10 power minus 2 seconds. So which is very quicker. Okay, so I said artificial neural network. It is uh, inspired by biological neuron. So before going into in deep about artificial neural network, once we have a look about uh, biological neuron. Okay, so before going to that, we'll once see the objectives of today's class. So here first we'll see what is a neuron, biological neuron, and after that how the artificial neuron is designed from biological neuron, and after that we'll discuss activation function. I said the data features will be collected and that will be processed, with activation functions, isn't it? So we'll see what are different activation functions. And perceptron. So what is a perceptron? Actually, perceptron, each unit in artificial neural network is called perceptron. So we'll see what is a perceptron, what is the functionality of perceptron, how the perceptron is functioning in the artificial neural network, what are the actions taken care in perceptron. Okay, so and after that we'll see how the network is implemented with neurons, and the implementation of with perceptron with the Python program. Okay, and here how the output is controlled with the internal components of the perceptron. Okay, and the next one. So this is our biological neuron. I said our artificial neuron is inspired from biological neuron system. Okay, so here biological neuron system, here you can see the uh, main body of the neuron system. This is also called the cell body or soma. Okay, the nucleus. So here this will process the input data given to this nucleus. The nucleus is used to uh, uh, process the input data. So the input data is nothing but coming from other neuron. So the other neuron is connected with the dendrites. So here these are all the dendrites of this nucleus. So these dendrites are connected with the other neuron outputs. Other neuron outputs are connected through synapses. So these are all called synapses. The edge of the synapses you can see. So these synapses produce the output of a neuron, and the neuron output is connected to the next nucleus through dendrites. So these are all the dendrites. These dendrites will receive the signal from the neighboring neuron. Okay, the neighboring neuron is connected with the help of synapses. So the synapses produce the output from neighboring neuron, and the output is received by dendrites of the neuron, and the dendrites will process the data, and the data will be sent to next neuron with a cable structure called axon. And this axon will carry the electrical signals produced by nucleus of the cell body, and that is transmitted to the next neuron with dendrites and synapses. Okay, the dendrites of the next neuron again will receive the output from the previous neuron. Okay, in the same way, here in artificial neuron also, you will have a neuron, artificial neuron, and you will have multiple inputs like this. Okay, the dendrites are the channels which will receive, not channels, they are connectors which will receive uh, from different uh, data. Okay, and the data will be processed here. Okay, and the data will be transmitted through various connectors. Okay, and these connectors will carry the information to the next neuron. See now how this is shown in the artificial neuron. So now for suppose you take an example. So the first one, 1957, Frank Rosenblatt designed this perceptron. So the perceptron, the original perceptron he designed, when he designed the perceptron, it looks like this. So these are all the input features are taken from training examples, and these are all sent to various internal units. They are called nodes. Okay, so and these nodes have some strength called weights, and the product of the input values and the weights are sent to some processing element like sum, and by with reference to some threshold value, the neuron is going to produce some output called f. Okay, and based on this f value, the program will evaluate which type of which type of output it is. Okay, the output reflects the classification of these examples. So all these things will discuss in detail in the next session. Okay, so here ANN, So it is the ANN inspired by biological neuron. So I just simplified the previous one. So this was the first uh, perceptron. Okay. So here, what is perceptron? Perceptron is nothing but an artificial neuron. So the each element in the neuron is nothing but it's a collection of neurons is an artificial neural network. So each neuron. So now, before understanding the artificial neuron, first we'll try to understand what are the components present in the perceptron. So this is our overall perceptron structure. So the perceptron contains several inputs. So the inputs are the training example inputs are given to the perceptron like this. So we have several inputs. So the first one you can say x0, x1, xn minus 1, xn. Okay. So I'll tell you why x0 is 1 always. It is always taken as 1. And weights w0, w1, w2, w3 and upon wn, they're all weights of respective inputs. Okay. So these weights generally the strength of the input signal. So how these weights are, these weights will play a very important role in driving the inputs to the output in a meaningful format. Okay. So here the product of weights and inputs will be passed to the next stage, that is a weight system. So the product of weight and inputs will be summed here, and that is transferred to the step function. The step function will evaluate the output in the form of classification. For suppose you are evaluating the input whether it is positive or negative. Okay, when you want to when you want to evaluate whether the input is positive or negative, then the first, so initially you are sending the features to the neural network, and these inputs are multiplied with the weights, and the products of input and weights are summed here, and that is evaluated by some step function, and the output, the step function of the output will be evaluated based on this weighted sum factor protocols. Based on some protocol, it will evaluate the input whether it is positive or negative. So we'll discuss in detail how it evaluates, how the weight plays important role. Okay. And how the output derives whether it is positive, whether the inputs are positive or negative. So here, this is the mathematical notation. As I said, in artificial neural network, the sum is here the output of weighted sum. Here it is the sum of products of input and weights, isn't it? Sum of products of input and weight. So that is here the input is 1 into W0. So that will be W0 plus X1 into W1 plus x2 into w2 plus xn minus 1 into wn minus 1 plus xn into wn. So the sum is transferred to step function. So here we'll see the mathematical notation w0. So here w0 x0, isn't it? X0 is always taken as constant. So here w0 is called bias value. See, what is this bias value? So before going to discuss the bias value, so here the perceptron will set a boundary between classifications. So for suppose here I said input, we are classifying the input, either it is positive or negative, isn't it? So here it will set, the perceptron will set a boundary between positive and negative classification, and this boundary is moved between the classification using this bias value. The bias value will control the movement of the boundary between the classification between the classification of the input. Okay, so here we have different products. So here, so to simplify the equation, I have set x0 as 1 and w0 I am taking as bias value, which is used to control the movement of the boundary between classification. So next, So for suppose here, if this is if for suppose if you assume this as one active function, okay, and if this active function is greater than 0, then the output will be classified as 1. And if it is otherwise, that is if it is less than or equal to 0, we can set it is classified as -1. Okay, so uh, here it is our, for suppose you this oral thing you can shorten with sigma I equal to 0 to n, where n is number of inputs. Okay, if it is greater than 0, it will be classified as positive, otherwise it will be classified as negative. -1, I'm representing the negative classification, and h is the hypothesis space where all uh, uh, required weights are the real numbered weights are uh, saved in the hypothesis space H. Okay, and how here these weights plays very important role in calculating the active function. So here how the weights are uh, selected, and that is very important here. Okay, so sometimes we can select the weights by randomly, and sometimes we need to train the perceptron to learn the weights. Okay, so the perceptron will learn the weights to adjust the boundary between classifications. Okay, next. So simply perceptron it takes all the instances in n-dimensional space. In the first slide, original perceptron, we have seen that is a two-dimensional space, isn't it? So it takes all input value, input instances from n-dimensional space. Okay, and in very common, perceptron can be used in many Boolean functions. So perceptron is able to we can use perceptron in implementing Boolean functions. Why we need to discuss Boolean function? Because in many digital operations and many digital circuits, Boolean functions plays very important role. For suppose you take any arithmetic operation, addition, multiplication, division, any arithmetic operation takes the help of Boolean functions, and gate, or gate, all these Boolean operations are there in the arithmetic operations. Similarly, in control circuits and in command circuits, isn't it? In any type of digital circuits, the Boolean operations plays very important role. So consider some Boolean functions like AND, OR, XOR. See here, when AND, these two are inputs. When the input is true and true, the output is true. When the input is true and false, output is false. When input is F and output is true, output is false. And when both are false, output is also false. So that means in AND gate, when two inputs are true, then only the output will be true. In the remaining cases, the outputs are false. So we can linearly classify the AND gate. So here true on one side and all false inputs are on other side. So these category we can classify like this, isn't it? So it is linearly classified. So similarly OR gate. When in OR gate, when the combination is, when the input combination is both are false, it is false, and in the rest cases the output is true. So here also you can classify the output like in linearly we can classify it, isn't it? So on one side false and other side you can place true, isn't it? For suppose you take XOR gate. In XOR gate, so here when both are true it is false, true and false it is true, false and true it is true, false and false it is false, isn't it? When the XOR input is F and input is F, the output is F. So in this case it is very difficult to classify, it is not possible to classify linearly, isn't it? So perceptron, as per our previous discussions, we have discussed that perceptron will classify the input either it is positive or negative. So when you give the input, the output must be like either it is positive or negative. So that is a linearly classified output. Okay. So but where in and OR we can do linear classification, but in XOR it is non-linear classification. So with simple single perceptron, we cannot classify complex circuits like XOR gate. we can implement simple circuits like AND, OR, NOT, and NAND, isn't it, like this? But XOR is not possible. Not only XOR, the other complex circuits we cannot implement with single perceptron. So this can be implemented with some more complex neural network. That is, by adding multiple neurons, we can solve XOR also. Okay, so those things also we'll discuss in the next class, multi-level neural network. And here, for suppose when you are giving some real world example, you take an example like just you want to classify, for suppose, a movie is good or bad. In that case, you can use only single perceptron. But when you want to classify at several categories, then again a single perceptron cannot be used. So for suppose you take an example like a customer need to be sanctioned loan or not, isn't it? So there we need multi-level neural network, because many features we need to gather, like salary, age, and whether he is a defaulter or not, isn't it? So several input features we will select, and all these input features are processed by hidden layer, and based on the hidden layer output, the output will be given to the active function. The active function will predict the classification of the user, whether the classification of the loan, whether the loan can be sanctioned or not sanctioned, or sanctioned with some conditions, isn't it? So all these are can be implemented. Complex operations, complex instances, complex classifications can be done with uh, multi-level neural network. So next, activation function. So I said activation function. So here where we are using this activation function, as I said, neural network, the features from input data, it collects all the features from the input data and process the data with some active functions and do classification of training examples. So the data will be processed with some active functions for doing the classifications. Okay, so here, based on the product, that is product calculated, uh, it decides whether the next neuron should be activated or not. Okay, so and also in what form the the input signal is processed, isn't it? And to which next neuron should be activated. The output of the previous neuron should be connected to which neuron, isn't it? So all types of outputs are generated at active function. There are different types of active functions. These active functions will take care about activating the neurons, converting the input signal of an neuron. Okay, and uh, the output of one neuron is input of which neuron, isn't it? So all these are evaluated by active functions. There are different types of active functions. Okay, so active function, selecting the active function at the right time, right at the correct requirement, it is very important. Okay, so types of active functions, there are mostly used active functions. The first one, binary step function or threshold activation function. So here, this activation function we use when the perceptron classifies uh, linearly classifies the output. Okay, linearly classifies the uh, output, like when it is greater than 0, it is 1. When it is less than 0, it is negative. Okay, something like that. When you are classifying only, when you have output in two formats only, positive and negative, or only two, A class and B class, then we go for threshold activation function. Okay, so here obviously the demerit, it cannot decide multiple classes like XOR gate, isn't it? I just gave a simple example. Okay, and similarly, when you are evaluating loan, isn't it? A person can be given loan or not given loan. or it can be given loan after clearing his past dues, or after submitting some documents, isn't it? So, or something with some constraint. There are different types of loan status of sanctioning, isn't it? So those things can be that those things multiple classifications cannot be done in activation function. For suppose in a binary step function. So for suppose when you are evaluating a movie, whether it is in when you are evaluating horror movie and romantic movie, action movie, isn't it? So there also binary step function may not work, isn't it, for complex evaluation of the movie reviews. Next, logistic function. In the logistic function, it ranges between 0 to 1. Okay, so where in the case of binary step function here, it is either 0 or 1, isn't it? 0 or 1. Okay, it is because it is linearly classified. And next here it ranges between 0 to 1. So here uh, uh, as a range between 0 to 1, generally when you are expecting the output in some probability, in that case we go for logistic function. And this logistic function generally mostly used in hidden layers. Okay, and here z is our so here this is our activation function. Okay, z is the sum of product, that is w0 plus w1x plus w2x plus wnxn, isn't it? That is our z. And based on this we can evaluate if the function, for we'll put some function, if pi of z is greater than 0, classify it as 1, if otherwise it is minus 1, something like that. We can set the ranges between 0 to n. So the when you are you can convert the output into probabilities according to the output produced at pi of z, isn't it? Next, when the main demerit here, when more negative input is given, then sometimes in most complex examples it will fail. Next, hyperbolic tangent function. In hyperbolic tangent function, uh, it ranges between -1 and 1. And here, the tangent function mostly used at output nodes, output perceptrons. So the problem in logistic function can be overcome in tangent function. Okay, and next, ReLU, it is mostly used in deep learning neural networks. It ranges between 0 to infinity, and there are some loosely fragile nodes, because of which there is a poor accuracy, and this can be, see here, this can be, so it is 0 till the value is always 0 till it is uh, the input is 0, isn't it? So here the active function value is always 0 when input is less than 0, isn't it? When it is greater than 0, then only it is going to increase, isn't it? So this the problem in ReLU can be uh, minimized by in, a new slope introduced in negative ReLU. Okay, so mostly leaky ReLU. This is called leaky ReLU, and mostly this ReLU is used in deep learning techniques. Okay, if time permits, at the end of unit, we'll see some examples about deep learning. Next, training the perceptron. So here, what is the need of training the perceptron? So as I said, so here the perceptron, go back to the perceptron. I'm going back to perceptron. So here the perceptron producing the output by summing the products of input and weights, and these weights will adjust. These weights will These weights are the strength of input signals, and here uh, uh, to get the desired output, we need to adjust these weights. Okay, so that the boundary between classification is exactly classified in correct way. Okay, so to classify, so for suppose I'll show the diagram. See, for suppose here this is our boundary between true classification and false classification. This boundary is will be correctly classified based on the weight adjustments. So these weight adjustments plays very important role in classifying true and false. So the perceptron will learn the weights to adjust the boundary between classifications. Okay, so here, so how to learn the weights then? How the perceptron will learn the weights? Why it is learning the weights? Because to adjust the weights to get the desired output. Okay, output means desired classification. So here there are two types of rules. One is perceptron rule and the second one is delta rule. In perceptron rule, here the way, as I said, the weights will be adjusted. For suppose when the desired output of the perceptron is positive, but you got negative, so what you need to do, you need to adjust the weight and again check the output. Still it is negative, again adjust the weight. So until it reaches to the, until it produces the positive classification. Once it is positive, then stop adjusting the weights, isn't it? So similarly here, you first give Wi, the initial weight. With the initial weight, if if it is able to produce the correct output, stop. Otherwise, add adjust the weight with some small delta W. What is this delta W? That is a small change in the weight. So the small change in the weight, it depends on the error produced in the output, isn't it? How this error is related with the small change in the weight. See here, the small change in the weight is equal to eta t minus O into xi. What is xi? The given input, and W is the weight we know, isn't it? And T is the target output, that is our desired output. For suppose I want to get positive classification. O is the predicted output. So whatever the output came after giving the sum of the products, isn't it? So that is the O. So here T minus O, target minus predicted output. And N is, what is N? N is the learning rate. What is learning rate? The perceptron learning rate with respect to the weights, isn't it? So this learning rate will adjust the amount of change in the weight, isn't it? So in most of the cases, it will be like 0 0.1, 0 0.01. Small adjustments with respect to the weights are happened because of this learning rate. Okay, we'll see the example also. Okay, so here delta W is a small change in the weight. Okay, so here the main goal of the perceptron is adjusting the weights to get the desired output or to minimize the difference between this T minus O, isn't it? Next. So here I just pointed the merit and demerit here. Okay. So the perceptron rule finds a successful weight vector when the training examples are linearly separable. That is correct, isn't it? So the weights will be evaluated correctly when it is linearly separable classification. Otherwise, it is failed if the examples are not linearly separable. In complex examples like loan sanction or movie classification, it may not, it will not classify, it will not able to predict the weights. Okay, where in the case of linearly separable classification examples, we can find successful weights. Okay, so the hypothesis space contains all successful weight vectors, real valued weight vectors. Okay, so this can be overcome the non-linear separable when it is failed in non-linear classification. In that case, we can go for delta rule. Okay, where the delta rule follows back propagation algorithm. Okay, so before going to uh, next delta rule, I just want to represent classification, linear classification and non-linear. Linear classification, for suppose all positives are classified here, all negatives are classified on the other side of the boundary, and this boundary is adjusted with the now bias value. I said the bias value, isn't it? And when you say mx plus c, y equal to mx plus c, y is the output and m is the weight and x is the input plus c is the bias. That bias is used to adjust this boundary with respect to the origin. Okay, so that it properly classifies the output. Okay, so here when such type of training examples, linearly separable training examples are given to the system, we can go for simple perceptron. Okay, but when the case like this, we cannot linearly separate this either like this or like this or like this. We cannot separate. Okay, see, if you try this like this, I cannot. This is not possible. This is not possible. This is also not possible. Nowhere you are able to classify, isn't it? Nowhere you cannot you can linearly classify the training examples, isn't it? So in this case, okay. So next, delta rule. Delta rule. Uh, I said when you are going for um, non-linear separable classification, we go for delta rule. Okay. So here it is uh, the delta rule works based on gradient descent algorithm, gradient descent technique, which is uh, uh, which is worked based on back propagation algorithm. Okay, and this is most suitable in non-linear separable classification. And here, based on the back propagation, that is based on the output, the output values are again feedback to the respective perceptron internally. Okay, so here the at the output the error will be calculated. So here the error in terms of weights are uh, is derived like half of sum of squares of the difference between target output of the training example D and actual output O of uh, training example D. So here TD is the target output of the training example, and O is the predicted output of the training example D. Here capital D is set of training examples. Okay, so we'll take some set of training examples, and D is the individual training example in the set D, isn't it? So here we are calculating the target output and predicted output at each individual training example, and we have to calculate the error, isn't it? So here, and the error, we need to minimize this error, isn't it? So to minimize the error, we need to adjust the weights, isn't it? So the error is with respect to weights, the error will be minimized. So we'll see how they are implemented. Okay, so for suppose here, as I said, the first one, perceptron. Here the perceptron uh, produce the output, and based on the weight adjustments, isn't it? If the output is not matching with the target output, then we need to adjust the weights and we need to observe the output. If still the output is not matching, then adjust the weights again, isn't it? So here, how these weights are adjusted? So one method, method that is select the weights randomly, and multiply it with input and sum it and find the output. If the output is okay, then note down the weights and feed the weights to the perceptron. Otherwise, if the output is not matching, the predicted output is not matching with the target output, then take next weight randomly. Okay, that is one method. And the next method we have discussed in the next slides, that is learning the weights, isn't it? So first we'll discuss learning the weights. Okay, select the weights randomly. See, I wrote a Python program for you, a simple Python program. So here, uh, I just took a program like see, for suppose here x equal to, it's a perceptron implementation that I will tell you. So here I took two lists. One is x list, that is input list. Input values I have 7.8 and 2. Okay, so for suppose you have two input nodes, one node is receiving 7.8 and the second one is 2. Okay, and here weights are 1 and 1. Okay, so here I hide the weight because here I'm taking weights randomly. Okay, so to access the weights randomly, so we need to import the package random. Okay, so initially I tested with fixed weights 1 and 1, isn't it? So with 1 and 1, and pass the X list, that is input list, and weight list. Okay, you can here I have set the fixed weights 1 and 1, and with this statement we can take the weights randomly. Isn't random dot sample range of -1 to 2. Between -1 to 2, take two ranges. Why I'm taking two readings? Because we have taken two input values, 7.8 comma 2. So for suppose two values, one is w1 and the second one is w2. So w1 into 7.8, w2 into 2, isn't it? And the sum will be evaluated. So here, uh, so then pass these two to perceptron. Okay, so first take the input values 7.8 x1, 2 x2, isn't it? And weights, either this is fixed weight and these are random weights. For suppose for the time being, you assume that we are taking the weights randomly. Okay, I hide this statement. This statement has no effect in the program. Okay, next I passed these two values x and wt, that is input and weight, to the perceptron. What the perceptron is doing? So initially the active function I set to 0. Okay, so here I passed x list and wt list, and zip will unzip the list. Okay, and I'm taking the individual values from x and wt. I is the individual value of the list. Okay, one time I will be 7.8 and the second time it is 2, and w is similarly the random weights. For suppose here random weights, it is displaying 1 and -1. Initially the w1 will be 1 and w2 will be -1. So for the first time I equal 7.8 and 1, 7.8 and 1. So that will be multiplied and added to f, isn't it? So f initially it is initialized to 0. So f equal to f plus w into I. Okay, so the values will be added to f. Okay, and as I said, if uh, so here I set the condition like if the active function is greater than 1, that means if it is 1 or above, that is positive, then it returns 1, else it returns 0. That means it is a one type classification. It is a classification 0. So it is a positive classification. If the output is greater than 1, that indicates that 1 indicates that it is positive classified. If it is less than 1, 0 or less, it is negative classification. Okay, I just set some condition like this. You can also put here f greater than or equal to 0, isn't it? If it is 0 and above, then it classifies at 1, isn't it? So based on our program, it will produce the output. So here, see, the weights are randomly taken 1 minus 1, and it puts the output 1. See, I'll show the output. New share. See, I have executed these programs in Jupyter Notebook. New share. Uh, okay. Okay. Here you can see the program Perceptron random weights. See here, I set the weights. So here I will hide this, and I will remove this. So I have fixed the weights 1 and 1. Let us see how oh, see here x I have taken two input values 0.5 and 0.2, and weights I have taken 1 comma 1. Okay, I'm passing x and weight to the perceptron. In the perceptron, I'm doing a product sum of products, and based on f value, we are classifying either it is positive or 0 type. Okay, so when the weights are 1 and 1, and I hide the random sampling, so here run the program. See here it is 0, isn't it? When the weights are 1 and 1. So let us take minus 1. When it is 1 minus 1, we'll see what the type of classification. Still it is uh, if you take it is input is 5, and see what will happen. Yeah, now the it is changed to 1, isn't it? So for suppose if the weights are 0, like this, we have to adjust the weights and see that whether the desired output came or not. See here, still it is 1. Okay, so for suppose if I set it is minus 1. Yeah, now it is changed to 0. Okay, so here by adjusting the weights, so here what I'm doing here, I've taken two input values and two weight values. So I'm randomly, manually changing the weight values, which is a cumbersome process. Here we have only two weight values. It is very easy, but in complex systems, we will have a large array of weights. So there we need to adjust the weights either randomly, or we need to train the perceptron to learn the weights, isn't it? So here I'll take the other case, that is I'm hiding manual posting of weights, and now I'm selecting randomly. See here, randomly when I tested it, it is 0, still it is 0, 0. So something like that, it will take the random weights and it will produce the output. Okay. So next, so here I have increased the number of inputs. So 7.8 to 2.5. So four input values and weights. So here weights also we have to take the same range. See here, either you have to take 1 1 0 1 like that. Okay, you have to take four weights. So here I'm hiding the manual posting of weights, and here I'm taking the weights uh, randomly. See, between -1 to 4, four random values we have to check, and I'm also displaying random weights here. When you run the program, see, random weights are 0 1 3 -1, isn't it? So here I'm also so here I just making the output more interesting. Here, whatever the 4 points I've taken, 7.8 to 2.5, they're all pointed in the training example space. Okay, I just want to make more interesting, just graphical interfacing, so that the user can easily identify his inputs on the screen, output screen. Okay, so here. I've used for plotting, I have used matplotlib. Okay, and in my matplotlib, I have imported the package pyplot to plot the wave. So here I'm plotting the wave between x and wt, input and weights. Okay, at the respective weights where the inputs are placed. Okay, and show and scatter is the second waveform. Scatter is for second waveform. Show is the plot will be shown to the user. Without show, you cannot enable the graph, isn't it? Okay, after show only you can you are able to see the plot between x and wt. And next, again, we'll go back to our slides. Okay, so this is with implemented Jupyter notebook and with simple two inputs. And here I've taken four inputs, okay, and four weights. And this is a graphical representation with matplotlib. Just I have given a small sample of the graph, how to plot inputs with respect to the weight changes. Okay, at each iteration, the weights will be changed and the graph also will change, isn't it? You can check. You have seen a different graph at the real time, isn't it? When I executed a different graph, you have seen, because the weights are changed. Weights are randomly selected. And next, here, but suppose here I'm taking 10 input data where the features are action, horror, and type of class. For suppose if the movie is of type action and it is horror, the movie classified, we need to classify, we need to derive the classification of the movie. For suppose I want to search, sorry, I want to search only all action movies. Okay, so for action movies, I'll put one. For horror movies, I'll put 0. So when the 2 points are, when action is 2 and horror is 2, so these points are evaluated based on some weights. Okay, action is 2 and horror is 2, then I classified it as 0. Okay, so when action is 1, horror is 2, it is 0. Similarly, when action is 7 and horror is 2, it is 1. Here also you can put class 1, 5, 4 and 1. I forgot to change here. And here, when it is 5 and 2, it is 1. But in this case, we have trained it as 0, so it will give output 0 only, isn't it? Next, it is 6 and 1, output is 1, so it is also an action movie. 8 and minus 0.2, it is 1. 7, 3, and it is action movie. So these are all the desired classifications in the model. So now we have to test the predicted output. If the predicted output is equal to desired output, it is okay. Otherwise, adjust the weights. Okay, until it reaches to until it matches with the desired output. So how many times we are iterating the adjustments of the weight? So here in the program, I have set for, as it is a small data set, so I have set for 5 iterations. Okay, see here, and predict uh, weights and row, also the same activation function. Okay, and next I have set the weights 0.1 for action movies, and this is for second one horror, and this is one classification, isn't it? The weights are taken like this, or suppose the fixed weights. Okay, so actually I already calculated the respective weights for every input, that is here in the data set. For every input I have calculated the weights, so that the desired the output will be matching with the desired output. I have already calculated, and actually system generated only. I wrote the algorithm, the learning rate. So, and I passed the rows and weights. So here the data set means here I put dot dot dot, don't put dot dot dot. This is the data set. This data, the list you have to place over there. Okay, so all these data set, all 10 inputs, and with respect to the rows from each data set. So each row will come from here. So this is the first row. Okay, for suppose first person given action 2 points and horror 2 points and classified it as 0. Okay, and that is the first row. Okay, and that is passed along with that is feed to the neuron along with the weights which I have already given. Okay, see how this is how I wrote the program, the prediction, and the data set. I wrote the all I feed all the data values here and the weights. Okay, so here actually I changed the data set, so I took a different data set, and this data set is also valid data set for this input. Okay, and this is a different input. Okay, so here I took these weights and I executed this, and I got the output like expected 0, predicted 0. So I got the same. See, if you change these weights, you won't get the predicted output matching output. Okay, so how I calculated the weights? For the human being, it is very difficult to calculate such weight values. See, okay, so we need to train the perceptron to learn the weights so that the predicted output will be matching with the predicted output will be matching with the actual output. Okay, see here. This is what we have discussed in the perceptron rule. What is WT plus 1? That is our delta W. What is delta W? Delta W is a small change in the weight, isn't it? We have seen that W equal to W plus delta W, isn't it? So in the initial slides, we have seen that formula, isn't it? So what is delta W? Delta W is equal to eta into T minus O into X, isn't it? See, long in the initial slides, we have seen that. So that is, this is our delta W. Delta W is equal to W plus learning rate. That is our eta, isn't it? And this is expected T. That is the actual output we need, and predicted T. So after giving the weights and input values, what is the output is computed, isn't it? This is the error into input, isn't it? The current input. So at each row is applied here the row values, and expected output either 0 or 1. We have seen, we have set some desired outputs in the data set and predicted what is the output calculated after feeding the weights. Okay, so that will be calculated. See the program here, the same perceptron. So training the weight. In the training weight, I have passed. Uh, so here you can check this. So this is our data set. All the data set, the same data set I have passed, and learning rate, isn't it? Learning rate. What is the eta? This is our eta value. Eta is 0.1. I said that means uh, at 0.1 steps the weights will be adjusted. Okay, and with n turn. So number of turns the training will be done for 5 times. Okay, and weights, and out of 5 times the best value, the best weights value will be taken. And for complex data, the n turns must be more, and wt is the weights calculated. See how that weights calculated by passing the data set and learning rate and also number of turns, and go here how the weights are trained here. Okay, all the training set, this is our training set. Okay, and next learning rate n and number of turns. Okay, so data set is trained, learning rate is 0.1, and n turn is 5 is passed to the function. And here weights are calculated based on the number of trains. See, there are for every turn we are calculating here. The formula is here: Wt equal to Wt of 0 learning rate into error. Okay, so the error is calculated here. Okay, so the actual output, whatever the predicted output, the predict function we have seen in the previous example, the predicted output is compared with the classification output, the actual output which is given in the data set. So that is matched, and that error is uh, calculated. So based on that, the error rate is calculated. See, the full formula is given here. This is our delta W. Delta W equal to delta W plus eta into T minus O. That is our error, and this is our input row of I. Isn't for individual input. So 2 2 1 2 5 4 2 1 like that, isn't it? And this is 0 1 0 1. That is all calculated by row of -1, isn't it? So here, after taking the weights, then I'm also showing the weight values for which you are getting the matching value. And next pass the this weight and row as usual, the old prediction value. Okay, so here predict the value when it is it returns 1 if activation I'll show the output. So here these are the number of turns for 5 turns, turn 0, and L rate is 0.1, and initial for the first iteration the error is 3, next iteration error is 3, next 3 on 1 it is after third iteration, fourth iteration error is reduced, and next error becomes 0, isn't it? So this is how the expected is 0 0 1 1 0 0. See, okay, and predicted is also 1. So how it is when the function is greater than uh, uh, 1, it predicts 1. If the function is predicts less than 0, it predicts 0, isn't it? So this is how we implement Perceptron. After thorough, in the next class we'll discuss backpropagation algorithm. In backpropagation, after discussing backpropagation algorithm, we'll implement a delta rule also. So, and in real world applications like identifying faces, recognizing speeches, and play games, autonomous vehicle drivings and robots, the artificial neural network is mostly used in these real world applications. Okay, so for suppose you take autonomous vehicle, there will be on the front side of the car, you will have um, 960 sensors, uh, and these sensors will read the features from the road, from visuals taken from the camera, and these inputs are given to these outputs of these sensors are given to 4 hidden inputs, and these 4 hidden inputs are given inputs to the 30 output units, and these 30 output units will help the car to move either sharp left or sharp right, or the direction of the movement of the car on the road. Okay, so the direction of the movement of the car is controlled by uh, the controlled by these sensors, and the sensor output is processed by hidden units, and these hidden units will feed the output to the inputs of these output units. Okay, so this is what the multi-layer network perceptron, which you are going to discuss in detail in the next class. So input layer, for suppose you take bank example. So for suppose you take one input person is, and the second input person salary, and you take some hidden inputs like defaulter. If he is a defaulter 1, if he is no defaulter 0, if he is paying regularly 1, isn't it? So these are the weights. For suppose weights are calculated in the hidden layers and multiplied with the input, and do some process based on the weights, and the outputs will be forward to next level of the perceptron. Here, for suppose it process all the data received from these nodes, and it will produce the output, like whether to sanction the loan to the particular person or not, based on the input features. Just here I just explained with the 2 features, but in real time you need to take multiple inputs. Like in autonomous vehicle, you are taking 960 sensor inputs. Okay, so which will act as retina for the car. Okay, uh, we'll discuss in detail about multi-layer neural network in the next class. Okay, and in the next class we'll discuss backpropagation algorithm, after which we can able to discuss delta rule, and after that we'll discuss multi-layer network, and if time permits we'll continue with recurring network. Okay, thank you.